We've talked about nucleophilic attack a lot. So in the classic SN2 reaction that we learned way back, like a month ago, we've got some alkyl halide, some bromide. My nucleophile attacks from behind. I end up breaking that bond and getting this new product with inversion. Now, here there are some kind of penalties to the cost, right? So I need to actually break a bond. That costs energy to do. There's also some steric hindrance here, right? So in the secondary halide, I've got to kind of fight through a little bit of traffic in order to get backside of that. There is another kind of nucleophilic attack that we're going to spend a lot of time thinking about here in organic too, and that is attack on a carbonyl. In a lot of ways, this is going to work out better. This is your most positive carbon. It's bound to the electronegative oxygen. So this nucleophile is going to really be drawn to that carbon. It's also going to be easier to get to because here this sp3 center is more crowded. This sp2 center is flat. So right away it's probably going to be easier for me to get this nucleophile close to that carbon just because there's 3 things around it instead of 4. Also, instead of breaking a sigma bond, here I only need to break a pi bond. This is different than the SN2 reaction. In the SN2 reaction, I'm attacking some sp3 carbon, breaking some bond to a leaving group. The leaving group leaves. Here, I'm attacking a more positive carbon that is easier to access, and I'm not breaking a sigma bond anymore. I'm breaking a pi bond, which is usually weaker. I'm getting to this tetrahedral intermediate. Again, when chemists name things, we don't spend a lot of time being creative. So we call this a tetrahedral intermediate because that carbon now has 1, 2, 3, 4 things around it. Sometimes this tetrahedral intermediate is stable. We'll simply protonate it and get the alcohol. But for now, I want to start by talking about cases where the tetrahedral intermediate is not stable. What if I have a leaving group already on that carbon? If I do, then this electron density can sort of fall back down. I can kick out that leaving group and get a new carbonyl with a new bond to some nucleophile. So that's the kind of reaction we're going to start with. Attacking some CO double bond that has some built-in leaving group. It's going to go a 2-step reaction. First the nucleophile attacks, then the leaving group leaves. It's not SN2, it's better. Okay, let's start with the most reactive of the carbonyl compounds that we'll see. So we've got acid chlorides and anhydrides. They are very, very similar in reactivity. I more or less think of these as exchangeable or interchangeable functional groups. So they're basically the same. Acetyl chloride, you really will not see Br here. Acetyl bromide is possible, but it's not very commonly used. It's too reactive. You will not see fluoride. You will not see iodide. So really the chloride is the sweet spot and the one that we'll use. So don't use the other halides. Acetyl chloride, acetic anhydride, both of them have a built-in leaving group. There it's easy to see. Here it's less easy to see. Here your leaving group is acetate, right? A pretty stable, weak base. Okay, how do these things get used? I'm going to give it some nucleophile. Very often just an amine or some nitrogen compound. This nucleophile will attack that carbonyl. This pi bond will now have to go, those electrons will have to go onto oxygen. I'll have some intermediate that looks like this, and now my leaving group will do the thing that it does. It will leave and give me a new carbonyl species that incorporates my nucleophile. Same thing for my anhydride. Some nucleophile will go after this one, Why this one and not that one? They're the same. It's symmetrical. Same or similar tetrahedral intermediate. This minus sign comes down. I lose my leaving group and end up at the same place. So really, really important. Really good way to make amides. So here's an example. I'm going to take some aniline, aminobenzene. Really important in the dye industry, especially way back when. So aniline will react with acetyl chloride. Draw the arrows. Nucleophile, electrophile, good electrophile. Lone pair, going to electrophilic carbon, pushing pi electrons onto oxygen, getting a tetrahedral intermediate. Here I'm drawing aniline attacking my acetyl chloride, but I don't need to deprotonate it first. So usually I would give it some weak base. Maybe, oh, I don't know. Maybe triethylamine. Okay? Is triethylamine a strong enough base to deprotonate aniline? No. The pK for aniline, I don't know offhand. I would guess probably in the 20s. It's going to be really, really hard for me to take that proton. All right? So I don't need to go to N- like that. I don't need to. All right? This is a reversible reaction. Okay? Now, you can probably guess that now that nitrogen is more acidic because it has a positive charge. So this nitrogen is not very acidic. This nitrogen minus is pretty unstable. But that N is pretty acidic now. It's got a full positive charge. Now it wants to lose a proton. This weak base will now take one of these protons from this intermediate. This is more or less irreversible because this is a much stronger base. This is a strong enough base that it won't go backwards. So let me recast this. This initial reaction is reversible. This neutral amine can attack this acid chloride and get to this tetrahedral intermediate. Now, which of these two are leaving groups? I've got this chloride that could be considered a leaving group, but I've also got this neutral amine that could be considered a leaving group. And if it loses the amine, that's just how it goes backwards. So at this first stage, this is a reversible reaction, and I can lose either this or that. But if I give it a weak base, and a weak base is all I need, I can take that proton and get to this. Now this is no longer a leaving group. N- is pretty basic. So it's really hard for me to think of this as a leaving group. This, though, is still a leaving group. So I will lose that chlorine and get to this amide. Acid chlorides can turn amines into amides. Okay, so we just went over how I can turn an amine into an amide by using an acid chloride. I can also use an acid anhydride in exactly the same way. I could also take an alcohol and use an oxygen as a nucleophile to attack some acid chloride or anhydride to get an ester. So this is also my way to make alcohols into esters. So here's an example. This is a very complicated natural product found in the poppy, the opium poppy. This is morphine. If I treat morphine with acetic anhydride, I'm going to form a diester here, right? The mechanism, so each of these OHs, so here I might use a base like triethylamine. And in this case, it is maybe more reasonable to say, yes, it's O- attacking my my anhydride. some intermediate like this. This is my leaving group, right? So I push my electrons up into the oxygen. O- comes back down, leaving group leaves, and that's how we get these esters. So this is a much more non-polar version of morphine. They thought it would react faster, and it does. They named it heroin because they thought it would be a heroic addition to the pharmacist cabinet. Maybe we don't think of it like that, but this is how you make heroin from morphine, is you treat it with an acetylating reagent, usually acetic anhydride with some base. So as they lay out in your textbook, what drug-sniffing dogs are smelling, are trained to smell, isn't heroin. It's the little bit of acetic acid that is the byproduct of this reaction, right? When this leaving group leaves, it leaves as acetate. And so what we're smelling for is a little bit of a vinegary vinegar, right? So vinegar is acetic acid. So again, we talked about amines into amides. We can also turn alcohols into esters with either an acid chloride or an anhydride.